previous experiments, we actually demonstrate two things. One is absorption, right? The sample needs to absorb the laser light. And then is the emission. We call it as the luminescence. So in the following, the chapter 4, we are going to talk about the interband absorption in the semiconductor. And in the following chapter, we are going to talk about the luminescence. Okay, so these two parts I will show you in the experiments. But here, I'm going to tell you that there's a terminology called the interband absorption. So what does it mean by interband? Interband represents between two bands. So what are those two bands in the semiconductor? What? Conduction band and valence band. Okay? So this interband absorption especially refer to the electrons from the valence band to conduction band, results in the interband absorptions. Okay? So in this chapter, we need to, first of all, to derive the absorption coefficients of these interband absorptions in the semiconductor. So, first of all, we have learned that the transition in the semiconductor about the interband, for the absorption, the transition rate is determined by this one. When you bump into this one, you will immediately know that this comes from the Fermi's golden rule. Okay? So it is determined by this one. Okay? This one contains the vector potential of the light. And also this one is the dipole moments. Okay? Dipole moment, this PCD is the matrix element, and A is polarization. And this delta function represents the resonant conditions. For the emissions, it's the same. Okay, for the emissions, the same. This coefficient is the same. So absorption rate and emission rate, they are identical. But now we assume that this transition, because it involves the optical transition, therefore their transition has to be vertical. Which means that if the electrons originally they have the wave vectors, that is kV. And then when it absorbs the light with energy h bar omega, then it will be excited to the conduction band. When the electrons in these points, their wave numbers or wave vectors has to be the same as kV. So this is the first requirement. And second requirement is that if these transitions occur, we have to make sure that there's an electrons here, there's an empty state here. But how do we determine whether electrons is here and whether there's no electrons here? That is determined by Fermi direct distributions we have introduced previously, right? So here is the Fermi direct distributions. Fermi direct distributions is especially determined by the Fermi level. So Fermi level, below the energy, below the Fermi level, you will find that the chance to find electrons is almost 100%. Above the Fermi level, this chance will very, very low. Okay, and previously we also show you that what this Fermi level relates to, what determines the energy of this Fermi level in the semiconductor. What parameter determines the Fermi level? The band gap? No, it's not the band gap. The Fermi level can be like Fermi level can be smaller energy or the higher energy, but no. But what parameters determines the Fermi level? So previously I said that these two things actually is equivalent. That we all refer to the same thing, is the carrier concentration. Remember that, right? So take this for example. If the Fermi level locates at here, it indicates that this semiconductor belongs to what? N-type, right? If the Fermi level locates at here, you will immediately know that this material belongs to P-type, right? For the intrinsic semiconductor, Fermi level locates where? The center, right? So Fermi level actually has to do with the carrier concentration. That will determine the position of this Fermi level. So once you know the Fermi level, we will know the probability to find electrons at here and here. So this is the first things we need to know to calculate this absorption and emission rate.